let me share my screen. Okay, let us start today's class. In the previous class, uh, we discussed deadlocks. Uh, I'll just go through 2 minutes and we will get back to today's class. So whenever a process is holding one resource and requesting for other resource, and that particular resource is held by another process and requesting for the another resource, when you're making a detecting a cycle, you can say that there are good chances of deadlock is happening. So you can avoid, you can prevent, you can recover the deadlock, but mainly you try to understand one thing, deadlock avoidance. In deadlock avoidance, we have to make sure that when you allocate in a sequence, uh, make sure that the system is in safe sequence. It falls into the safe sequence. If the sequence is not safe, then there are good chances the system will go into deadlock. For example, let us see this example T0, T1, T2. You have this needs. We studied this example. T0 is holding 5 resources, T1 is holding 2 resources, T2 is holding 2 resources, and only 3 free resources are available. These 3 resources, if you allocate to T0, which is 5, so it will not finish its job, it will go into deadlock. If these 3 resources you allocate to T2, then also this will go into deadlock. But the safe sequence is, if you allocate first to T1, then out of 3 resources, 2 resources, if it is finished, then the remaining resources will be free. Then 4 plus 2, 6. These 6 resources you can give to T0 because it's only needed 5. Then you will get the maximum number of resources 10 and you can allocate to T2. The sequence in which you are allocating the resources makes your system safe, which will not make you enter into deadlock. Okay, so in which order you are allocating the resources, the sequence matters. So that's what the safe state. Whenever you are allocating a resources to a particular thread or a particular process, make sure that the system is in the safe condition. And the safe is in which order you are allocating the resources. If the system is not safe, surely the system will go into deadlock. If the system is in safe, then there are chances that you can avoid deadlock. Okay, we studied 2 mechanisms. One is deadlock avoidance using resource allocation graph and Banker's algorithm. Whenever you are allocating a resource, if it is making a cycle, then don't do that. This is one method we can avoid the deadlock. Before allocating, before allowing the resource, you check, verify once if it is making a cycle or not. If it is not making cycle, then you allocate. If it is making cycle, then don't allocate. But Banker's algorithm works even in a better way. It works in multiple instances. Suppose you have say 5 threads, allocation graph, and this is the maximum graph, maximum required resources. The need, you can calculate max minus allocation. Okay, max minus allocation will give you the need. Now these are the available resources. You don't allocate these resources to T0 because T0 A type required 7, but we have only 3. Although you cannot allocate any resources which are not the needed is not met with the available. If we allocate this available resource to T0, then system will go into deadlock. But you can allocate this into T1. So T1 is meeting this requirement. After meeting this T1, this all the resources will become free. Then you can allocate to other resources where it will finish its job and come without entering into deadlock. So the sequence in how we are following, we need to make sure that that is a safety algorithm. And once you do that, you allocate the request resource. So if the request is less than need, if request is available, then allocate it. If either of these condition fails, don't allocate. So in this way, you can avoid the deadlock. The Banker's algorithm is very much predominantly used algorithm to avoid the deadlock in operating system. Is this clear?
Yes, sir.
Okay. Now, today's class, we will discuss about memory management unit. We will discuss about memory management. So, memory management is one of the important things that is handled by the operating system that we need to look into it. Now, in memory management, there are two things. One is main memory, another one is virtual memory. So in this week, we'll discuss about main memory issues, and next week, excuse me, we'll discuss the virtual memory. Um, we will be not able to finish today's class the main memory, but we'll continue this discussion in the Thursday's class also. But let us see that how much we can cover in today's class. So main memory is the central operation of modern computer system, right? And main memory consists of large array of bytes, each with its own address. CPU, when it's executing its instructions, it will take those instructions from the memory, and typically that instruction will be fetched from memory. When I say that instruction execution cycle, when an instruction execution cycle, what it means is these instructions are executed from the memory, it will be fetched from the memory, that instruction is decoded and cause the operands to be fetched from the memory. Then after calculating, after the instruction is executed, the results are stored back in the memory. Okay, the instructions are executed from the memory, decoded and cause the operands to be fetched from the memory, and the results are stored back in the memory. So the memory units and the register that are built in the processing core, which are directly accessible by the CPU. The processor will access the registers and the main memory directly. These are there are machine instructions that takes memory address as arguments, and when an instruction is executing, any data being used by the instructions can be one of the direct access storage devices. If the data is not available in memory, then if CPU want to execute them, if CPU want to operate on them, they should move first to the memory, then only it will execute. If data is not in the memory, then CPU cannot operate on them. First, they should be moved to the memory, then only the CPU can operate on them. For example, let us say that this is a typical example where the main memory looks like. So some amount of space will be occupied by the operating system, some amount of space will be taken by operating system, and each process will be allocated for that particular amount of memory. Okay, now let us say that each process should be having unique address space, a separate address space we should be allot for each process, and each process should not interfere with other process. Okay, so how we'll decide that is based on two values, that is a base register and the limit register. Okay, that is a base register and the limit register. For example, the base address for that particular process is say that 3,40,000, and this process it needs say like 1,20,900 bytes of memory it is required. Then this base address from the amount that is required will be added. Base plus limit will give you, the base address is 3,40,000, the limit address is 1,20,900. This both address will help us to allocate the process from which memory location to which memory location this process need to be allocated. Okay, so all the memory locations for this process will be accessed from this memory locations only. 3,40,000, 3,40,000 to 4,20,940 only they will be allocated. Okay, is this clear?
Yes, sir.
We call them as a legal address. So to separate memory spaces, we need the ability to determine the range of legal addresses that process may access to ensure that process can access only this legal address. This process should not interfere with this process address. This process should not interfere with other process address. When you're trying to access other process address, that is illegal. Okay, so we will make sure that the process will use only the legal address space based on these two values, base and limit addresses. Now, whenever we need to protect the hardware addresses using this base and limit addresses, whenever a CPU is generating some address, this address should be greater than or equal to base and should be less than base plus limit, right? This address should fall within this range only. So it should be greater than or equal to base, and it should be less than base plus limit. So the CPU's generate address, it should be greater than or equal to base, and it should be less than base plus limit. If this both conditions true, then only it will be accessible in the main memory. Either one of this condition fails, then we will declare that trap to operating system illegal addressing error. So this scheme prevents the program accidentally or deliberately modifying the code or a data structure of either operating system or other users. So if this process should not go into operating system, it should not disturb the process that is executing in the operating system, right? So the base address and limit address can be loaded only by the operating system, and when an CPU is generating some address, it should verify this base address and base plus limit before accessing the main memory. Is this clear?
Sir, the base and the limit are allocated by the OS, or they are predefined according to the RAM space?
Operating system. Operating system. The base and limit address registers can be loaded only by the operating system. Initially, when a process is generated, and for a particular program, this many address locations are required, then the operating system will decide this process can be allocated from this address location to this address location. The base address and the limit address can be loaded only by the operating system. Operating system will decide.
Okay, sir.
Okay. Now, typically, this is how the user program will be generated, right? You have a source program. In source program, you will compile and you will create an object file. The compile time will help you to generate your source program into an object file. This object file further linked with other object files using linker, converted into executable file, and it will be loaded for execution. And when the program in the memory dynamically linked libraries with this, and the program executable file will be loaded, and this is called execution time. So we have compile time, we have load time, we have execution time. When a program is generated, that amount of program for that particular program, the memory space that is available should be handled using address binding. Okay, so addresses in the source program are generally symbolic. For example, variable count. You declared, suppose int is equal to 5, int is equal to 10. Then what it says that your program is declaring some variables. A is equal to integer variable, and that integer variable, if it takes 2 bytes or 4 bytes, those many memory locations should be allocated in the main memory, and that address binding should happen. Okay, so this compiler typically binds these symbolical addresses to the relocatable addresses. Suppose 14 bytes from the beginning of this module. Then the linker or loader turns this bind relocatable address into absolute addresses. What is this? We will try to understand. Okay, each binding is a mapping from one address space to the other address space. So whenever we need to understand first three things: this, what is compile time, load time, and execution time or runtime. If you know that at compile time where the process will reside in the memory, the absolute code can be generated. So that is the object file. Absolute code will be generated in the compile time. In the load time, this absolute code will be loaded into the memory for execution. Suppose if it is not known at the compile time when the process will reside in the memory, compiler must generate relocatable code. If the process can be moved during its execution from one memory segment to another, then binding must be delayed until the runtime. So there are many parameters we need to consider when an address binding happens with respect to compile time, load time, and execution time. Now, here I told that when an address is generated, it should be mapped from one address space to other address space. What actually that meant is, we have in operating system two addresses. One is logical address and physical address. The address generated by the CPU is commonly referred as logical address. Usually the CPU will generate some address that will be our logical address, whereas the address seen by the memory unit, that is the physically available address, the one loaded into the memory address register of the memory, we commonly refer that as a physical address. So a runtime mapping from this logical address to the physical address is done by a hardware device. We call that as a memory management unit. Okay, so typically we have two addresses, logical address and physical address. Logical address is generated by CPU, physical address is generated by it's there in the main memory. So this conversion can be happen from logical address to physical address by memory management unit, which is a hardware device. Is this clear?
Yes, sir.
Now let us see this. The binding addresses at either compile time or load time generates identical logical and physical addresses. But execution time address binding scheme results in differing logical and physical addresses. Usually this logical address is referred as a virtual addresses. So execution time address binding scheme, at execution time the physical address and logical address are different. At compile time both seem same, they are identical. But the set of logical addresses generated by a program is called logical address space. The set of all physical addresses corresponding to this logical addresses is physical address space. Thus, in execution time address binding scheme, logical address and physical address differ. They both are different. So, whenever a user program deals with logical address, whenever I'm writing a program, whenever a user is writing program, usually what he does is he deals with logical addresses. Whenever memory mapping hardware converts this logical address into physical address, the memory management mapping hardware converts this logical address into physical address. We have two types of addresses. Logical address, for example, a program Now it is taking, say, program.c, it is taking, say, 20 bytes. Okay, then the logical address sees that the program may take maximum 0 to 20 bytes. Here max is, say, 20 bytes. So this program will take maximum 20 kilobytes of memory. That's how we will see that logical addresses. It will be in the range of 0 to max. But physical addresses, we need a base value or some base value range where from which memory location the physical memory is available. From that memory location, r plus 0 to r plus max is the physical address range. So user program generates only logical address. Think that process runs from 0 to max, but whereas this logical address must be mapped to the physical address before they are used. For example, here dynamic relocation using reallocation register happens using simply like this. Suppose the base register is also called as relocation register. The base register relocation register is 1400. Now the CPU generates a logical address of 346. Now what happens? The memory management unit, it will add 14,000 plus 346 and it will say that the memory location is at 14,346. Means the range of logical address is 0 to 346. The physical address, the space available, the base register or relocation register is 1400. So the address is allocated from 1400 to 14,000 to 14,346. So now the physical address will show that the address is 14,346. Here the base register relocation register, that is the R. R is the base value R or relocation register is 14,000. Okay, this address is generated by CPU. Is this clear?
Yes, sir.
Now let us revise this address binding. So whenever a compiler typically binds these addresses to relocatable addresses, and the linker, the compiler typically binds addresses, the symbolic, the variables that you declared. Suppose int a is equal to 5. This a is equal to 5. Compiler will bind this a is equal to integer a into relocatable addresses. That is, relocatable addresses are generated by relocation register, means that the process that is generated. Okay, the compiler will do this. The linker or loader binds this relocatable address to the absolute addresses. Binding mapping, each binding mapping is one space to the other space. Compile time, if you know the compile time where the process will reside in the memory, it will generate the absolute code. Load time, it will generate a relocatable code. If this relocatable code is not available in the memory segment, it will be moved from one memory segment to another memory segment, makes a delay in the runtime. Now this logical address that is generated by the CPU, that is a programmer, usually that is generated by the programmer. User program deals with the logical address. This address is same when a binding address happens at compile time or the load time. Identical logical addresses. But the execution time, when it makes into execution time, they are different because it will now the logical address will be changing into physical address. Okay, because execution, when it happens, the processor will generate some address which is logical, that is relevant to the program or the programmer that who's doing, but physically the memory location might be different. That will be different when you run the program. So the logical address will be mapped to the physical address before they are used. Usually user program generates only logical address, but actually physical address we need to consider from the available memory space in the RAM. Based on that, in the main memory, based on that, we have to take care of that. So there is a difference between compile time and execution time. Is this clear?
Yes, sir.
So at compile time, only we will worry about logical register, but at execution time, physical address matters. Okay. Now let us talk about continuous memory location. Now, if you observe that here, uh, the process operating system takes some space. After that, each process is occupied by particular some memory location. Now, whenever we are allocating some process, we are allocating in continuous memory locations, and sorry, and one after another we are allocating continuously. Okay, so we can allocate from the base address. You see that 0 to maximum, this is 10 lakh, right? 10 lakh. So this many memory locations we are starting from continuous one after another. Now we can either start from high addresses to low address, or we can start from low addresses to high address. When it comes to continuous memory location, uh, this memory location usually divided into two partitions. One is by operating system, other is by user process. So some part of memory will be occupied always by operating system. The remaining memory space will be allocated for the user. We can place the operating system either in the low memory addresses or high memory addresses. And the operating system where we can keep low memory or high memory depends on the various factors uh, that are location of the interrupt vector and so on and so forth. But many operating systems, Linux or Windows, they place the operating system in the high memory. Therefore, we'll discuss the situation only. If you observe this in this example also, the operating system is kept in the high memory locations. It is we can keep from 0 to some memory locations, and allocate the remaining process for the rest of the memory. Excuse me. Or else we can allocate the operating system to the higher memory address. Usually nowadays Linux and Windows, they both allocate the operating system in the higher memory. From 0 to the rest of the remaining available memory will be allocated for the user process. But you can allocate either way. uh, it depends on the various factors. However, it is observed that keeping at the high memory will be more helpful or more efficient. So in continuous memory location, each process contains a single section of memory, that is continuous memory location, and the next location, next process is for other, next location is for other process, next section is for other process. Now suppose you have a memory location, say okay, I will explain that. Okay, suppose you have a memory location, you allocate p1 here, you allocate p2, p2 here, you allocate p3 and so on and so forth. So each process should not disturb the other process. We allocated this is process p1, say this is process p2, this is process p3. Each process has its own continuous memory locations. It will not interfere with other process. Okay, that's what we have to keep in our mind. Continuous memory location, each process contains a single section of memory that is continuously available to the section containing to the next process. Now we cannot allocate some part of process here and suppose we cannot allocate process p1 some amount of space here, and we cannot allocate p1 some amount of space here. We cannot do that. Okay, we should allocate the continuous memory space. Okay, now we will talk about memory location, memory protection. Whenever a relocation register contains, the relocation register contains the smallest physical address, and the limit register contains the range of logical addresses. For example, relocation says that this is the address, the limit says this is the address. The logical address that is generated should fall within the range specified by the limit register. Memory management units maps this logical address dynamically by adding the value of relocation register. This memory is mapped is sent to the memory. For example, the logical address that is generated by the CPU, will be verified whether this falls less than the limit register or not. If it is less than the limit register, then only it will be allowed. Otherwise, we will generate a trap addressing error. Excuse me, guys. Then it will be allocated to added with relocation register to generate the physical address. So this relocation register will be added with the logical address and with the limit register to store in the physical address. Okay. So the memory management maps this logical address dynamically by adding the value in the relocation register. Okay, the logical address must fall within the range specified by the limit register. So we will make sure that the logical address, whatever is generated, will fall into the range of limit register. If it is no, then we will generate error. Otherwise, we will add the relocation register plus the logical address to map into the physical address. Is this clear?
Yes, sir.
Now, there is an interesting concept called memory allocation. How we will allocate the memory for that particular process. Now, one of the simplest way for allocating memory is to assign the process variable size partitions in memory, where each partition may contain exactly one process. For example, let us say that this is the high memory and this is the low memory. Operating system is here, and you allocated process P5, process 8, process 2, and so on and so forth. Okay. Now, after some time, say that process 8 finished its job. It created this hole. This memory space is available. We can allocate for the new coming processes. Let us say that process 9 came and it is allocated in this space. Again, some memory space is available, and after some time process 5 finished its job, then some more spaces are available. Initially all the memory spaces is available. It is a big hole. Now, as eventually as the time passes, it will create a variable size holes. This is some amount of memory, depends on process P5. This is some amount of memory which is used. So these are variable sized holes. Okay. So the variable size partition scheme, the operating system keeps a table which parts of the memory are available, which are occupied. Okay. Here it says that from this memory location to this memory location is by operating system. This memory location is available. This is occupied by process P9. This is available. This is occupied by P2. This all the information will be kept in a table by operating system. Now, initially all the available memory for the user process is considered as a one large block of memory. We call that as a whole. But eventually you will see that memory contains a set of holes of various sizes. Okay, this is of different size, this is of different size, depends on the process. Is this clear up to this point, how the variable partitions are created?
Yes, sir.
Now, how we are going to allocate a particular process under which block is again a question. Suppose let us say that we have this, we have say that these are available blocks, freely available blocks. Let us say that we have P1, P2, P3, P4. We have 4 process. Let us say that we have block 1, block 2, block 3, block 4. Okay, let us say that block 1 is of 10 kilobytes, block 2 is of 20 kilobytes, block 3 is of 30 kilobytes, block 4 is of 40 kilobytes. Now let us say that P1 requires 5 kilobytes, P2 requires 10 kilobytes. This is program 1 or process 1, you can assume anyway. Process 1 needs 5 kilobytes, process P2 requires 10 kilobytes, process P3 requires 15 kilobytes, process P4 requires 20 kilobytes. Now, which process P1 can go to block 1, block 2, block 3, block 4? It can go in any block, right? Suppose P1 is going in block 4. Okay. Now, P2 can also go to 10 kilobytes. It can go to block 1, block 2, block 3. It can go in any block. Let us say that P2 is going to block 3. Now, P3 cannot go in block 1 because P3, in order to finish, you need 15 kilobytes, but B1 is only having 10 kilobytes. You cannot put it in this block. You have to keep in block 2, right? P3 will go into block 2. P4 needs 20 kilobytes, but only available space is block 1, 10 kilo, which is not free. So it will not allot. So you have to keep waiting. Either one of this P2 or P3 or P1 will finish this job. Until that, P4 cannot allocate. So in which order this process should allocate in which holes, which blocks, is again a big problem. When it is in a continuous memory allocation, which means all the process entirely you should allocate completely to that particular block, it will create a problem. Now here, when P1 is allocated in block P4, how much of memory is left unused?
35 kilobytes.
So because the block P4 takes 40 kilobytes, P1 needs only 5 kilobytes. So unused space is 35 kilobytes. Right? So here again, like that we can calculate. So there are various strategies are available. Dynamic storage allocation problem is what concerns how to satisfy the request of size n from the list of free holes. We have three strategies: first fit, best fit, and worst fit strategies that are commonly used to select a free hole from the set of available holes. First fit says that allocate the first hole that is big enough. So you keep searching for the available blocks, and for the particular process, whenever you see that this block will fit, then you allocate it. Whichever comes the first satisfying block, you allocate it. Searching can either beginning from the set or the location where the previous first is searched. We can stop searching as soon as we find the large hole. Best fit says that allocate the smallest hole that is big enough. Okay, allocate the smallest hole that is big enough. We must search the entire list to make sure that which will give us the smallest hole that is big enough. And this strategy produces the smallest leftover hole. Worst fit says that allocate the largest hole. Whichever is available, you allocate the largest hole. Then also for this, we need to search the entire list unless it is sorted. So this strategy produces largest leftover hole. Largest leftover hole means here, in this case, if process P1 is going into block B1, if process P1 is going into block B1, then also 5K will be needed. How much is unused space?
5K.
5K. That is called leftover space. Okay. So the leftover space will be maximum if you allocate as per the worst fit. Worst fit says that allocate the largest hole. So 5K, when a process, the largest block is 40K, when you allocated that, it generated 35 kilobytes hole, largest hole, that is not good. Here it is generated the smallest hole. Best fit generates the smallest hole, that is only 5K. So best fit will generate the smallest leftover hole. Worst fit will generate the largest leftover hole. We will discuss this best fit, first fit, worst fit with an example. Let us say that we have job 1 and job 2, job 3, job 4, which requires, job 1 requires 90 kilobytes, job 2 requires 20 kilobytes, job 3 requires 50 kilobytes, job 4 requires 10 kilobytes. Now we have blocks, block 1, block 2, block 3. Block 1 is of 50 kilobytes, block 2 of 100, block 3 of 90, block 4 of 200, block 5 of 50 kilobytes. First fit method says that you take the job, you see that wherever there is a large enough, you keep it. First fit says that allocate the first hole that is big enough. So 90K will search block 1, this is not sufficient, it will not allocate. 90K will search block 2, this is sufficient, it is matching. So block 2 is allocated for job 1. Job 1 takes block 2, the unused space is 10K, correct?
Yes, sir.
Now job 2, 20K will come, 20K will search, this is occupied, this is free, this is free. So 20K will fit into block 1, yes. So you allocate block 1 to job 2. Job 2 will be taking block 1. So the unused space is 50 minus 20, 30 kilo units. Job 3, you cannot allocate in block 1, block 2. Job 3, 50K can be allocated in block 3. This is large enough, sufficient enough. So block 3, job 3 can be kept in block 3. You can keep here. Then 50K minus 90K, the leftover space is 40K. Job 4, you cannot allocate in block 1, block 2, block 3. It can come in block 4. This is sufficiently large enough. You can allocate job 4 in block 4. Job 4 will go in block 4. The unused space is 190K. This is null. This is not used yet. Okay, you understood how the first fit method works?
Yes, sir.
Now the best fit method works. Let us try to understand the best fit method. Best fit method works that allocate the smallest hole that is in the big enough. That is big enough. We must search the entire list. So in best fit method, 90K is there. 90K will search block 1, 50K. This is not sufficient. It will search 100K, but here their unused space is 100K. So 10K is unused. This is it will keep note down. 90K will keep searching block 3. Block 3, if you search the unused space is 0. Block 4, job 1 again search block 4. Here if you search the unused space is 110. You cannot allocate in block 5. Among all these blocks, the smallest unused space comes in block 3, 0 units. So job 1 will take block 3. Job 1 will allocate it to block 3. And unused space in block 3 is 0 bytes, 0 kilobytes. Job 2 will likewise search. The unused space here is 30K. The unused space for block 2 of job 2 is 80K here. If you allocate here for block 4, this is 180K. Then here also, this is 30K. So you can allocate in block 1 or block 5. So it will allocate in block 1 or block 5. So job 2 takes block 1. Job 2 takes block 1. The unused space is 30K. Now job 3 will come. Again, job 3 will search. You cannot allocate in block 1. You cannot allocate in block 3. It will search here block 3 for 50K. The unused space here it will be 50K. The unused space here will be 150K. The unused space here it will be 0. So block 3, job 3 will go to block 5. Job 3 will go to block 5. The unused space is 0. Job 4, 200 kilobytes. None of them you will allocate. Block 4 is sufficient enough. Unused space is 0. Block 4 will be taken by job 4. And block 2 we haven't used. So it is not used. So the available space is none. You see this? The best fit method allocates the smallest units possible. It will generate the smallest leftover. Is this clear?
Yes, sir.
The worst fit method says that allocate to the largest hole. Allocate to the largest hole. So 10K will search the largest hole in the available blocks. 10K, the largest hole is 200K. So job 1 will take block 4. Job 1 is allocated to block 4. It will generate the largest unused space. So 10K is allocated to block for 200K. The unused space is 190k. Job 2 will take the second highest. Among this, the second highest is block 2. So job 2 will go to block 2. So job 2 is assigned to block 2. The unused space is 80k because 20 minus 100, 80k. Job 3, next highest is block 3. It will go take block 3. Job 3 will take block 3. The unused space here is 90 minus 30, 60k. And job 4 is having 70k. You cannot allocate in block 1. You cannot allocate in block 5. You cannot allocate in block 1 or block 5. It has to wait for the other process. So the worst fit method says that whichever has the largest space, you allocate it. Then the unused, the leftovers, it will create the largest leftovers. That is largest leftover hole. Okay. Now, whenever you are allocating some space, for example, here in this case, um, job 1 is allocated to block 2. Block 2 is having 100k, but job 1 needs only 10k. The unused space 10k, the unused space 10k, we call this as fragmentation, external fragmentation. Okay. Suppose in this case, block 1, 10k is allocated to block 4. Okay. Now, the unused space is 190k, but this 190k available space, job 4 needs only 70k. We have space 190 kilobytes which are free, but you cannot allocate job 4 to block 4 because this block is occupied by job 1. Okay. You have memory available, but still you cannot allocate because this block is occupied by another job. We call that as an external fragmentation. External fragmentation. You have space, but you cannot use it. Sorry, I'm writing with my mouse. The spelling is not correct. So the fragmentation, it can create internal, it can be external. Okay, the fragmentation can be internal as well as external. We'll discuss that in detail in the next class. How this fragmentation we will handle, we'll handle that in next class. But in continuous memory allocation, based on the job and the memory available, when you allocate them, it will create external fragmentation. The memory is available, but still will be not able to use it. Is this clear?
Yes, sir.
Is there any doubts up to this point when you are allocating some first fit, best fit, worst fit? Up to this point, fragmentation we'll discuss in the next class. If you have any doubts up to this point, you please ask.
Sir, is worst fit used in general?
No, generally we will use best fit or first fit.
First. Okay.
But why can't? If the application demands that worst fit, you can use it. But there are 3 mechanisms possible. That's what we discussed that. Okay.
Okay, sir.
Okay. So let me upload the slide. Verify that the slide is visible or not. If you have any questions, any other doubts, please ask. I uploaded the slide, lecture 22 memory management. Can you see that the slide is visible? Can you verify that slide is visible or not?
Sir, it is not came yet.
Sir, it is visible.
Okay. So lecture 22, memory management. You can see that it would be visible. All right, go through the slides. If you have any doubts, we'll discuss on Thursday's class. We'll stop here.